All right, so we have a diagram of a vapor compression refrigeration cycle here. We're given all the properties that we could possibly need, and really the only thing that we need to do is get our governing equations and start plugging things in. So the first thing that it asks us to find is m dot 5 in kilograms per minute. So that's the mass flow rate of the refrigerant through the evaporator. So all I need to do there is apply my energy balance to evaporator 1, and I know what Q dot N is, Q dot N1 is, and I know that it's I know the energy balance will give me Q dot N over H5 minus H6, and I've got H6 and I've got H5. It's just a matter of plugging things in and making sure I've got my unit conversions done correctly. And then part B is asking for the compressor power. So the compressor power, it's m dot 1 times H2 minus H1. Now at this point I have m dot 5, but I don't actually have m dot 1. So I want to make a note where the mass flow rates are the same. So you can see the mass flow rates are the same at 2, 3, 4, and 1. That's not written on there, but 1, 2, 3, 4, and then 5 and 6 are the same, and 7 and 8 are the same. So I need to figure out what m dot 1 is. So I need some way to relate those mass flow rates. So what I'm going to do is I'm going to pick control volume in which all those mass flow rates are involved. And that's that little section of piping that I've kind of highlighted here with the red dotted line. So what it is going to be the stuff coming in. If I apply my conservation of mass, it's going to be the stuff coming in is equal to the stuff coming out, because dmdt is equal to 0. So the stuff coming in, I've got things coming in at 4, so that's my m dot 4. And then what you'll notice, the stuff that's going out, so what's going out of that control volume that's moving to the right, that mass flow rate, even though there isn't a number right there before it goes into the evaporator 2, it's the same mass flow rate as state 7. And likewise, going down, it doesn't have a number there, but it doesn't matter because it's the same mass flow rate as at state 5. So 5 and 7 are going out, 4 is going in. And so now I've got something that relates those things. I also maybe want to switch things around to where it's in terms of m dot 1. And let's see, so I know m dot 5. I need m dot 1, which means I need m dot 7, and for that I'm going to do an energy balance on the second evaporator. So if I plug things in, I can get that mass flow rate. Now you'll notice that H4, I used H4, and that's because in my little control volume there, going in, it's got an enthalpy of 4. Going out, it's also got an enthalpy of 4 because nothing's really going on. We're not adding energy or taking energy away in the form of heat transfer. All this stuff is insulated. The piping and everything is insulated. So the enthalpy going into the evaporator number 2, is H4. So if I plug things in, I get 4.823 kilograms per minute. And from there, I can calculate m dot 1 and get my power required for that compressor. Then I need the rate of heat transfer for the refrigerant passing through the condenser. Easy peasy. I'm just applying an energy balance to that condenser, plugging in my H values that are given to me, and that's it, 22.91 kilowatts. All right, well, I hope that was helpful. Thank you very much for watching, and let me know if you have any questions.